lot of information. So Holtz and Ekin suggested that you should use only the second lag and put others as 0. But what is the problem in doing that? The real problem is that a lot of information get lost. A lot of information is lost. Or
excuse me.
Yes.
I have one thing to tell the organizers. Can you just focus the camera to us, sir? Because we are not understanding most of the things. Because since sir is using the board also, so please cooperate.
So you cannot see the. Can you see my? Oh. Basically,
we can see your PPT,
I'm using
but we can't
yeah, I understand what you're
actually
saying. I'm using the pointer here. You are not able to see that, isn't it?
Sir, actually we can see the PPT. We are asking you to focus the camera towards you actually. So that you are also using the whiteboard, right? So that's why we are making
whiteboard.
Notes.
Okay.
Yes.
So you can't see me now. Can you see me now?
No, sir. No, sir.
That's sad. You have 2 cameras and you can't see me. Oh no, 4 cameras. And you can't see me.
Camera is voice sensitive. Where you speak, that camera will catch you.
Okay, so I should stand here. Can you guys see me now, those who are online?
No, sir, we can't see you.
Why the organizers fix that? So basically, this is what Holtz and Ekin suggested. yi1, rest everything 0. If we are using 2 periods lag, yi2, rest all 0. We can add more, but you can include that also in the system. But what is important here is that since you are using only the second lag, you are losing out a lot of information because all lags have some explanatory power. That is idea behind the dynamic panel model, right? Yi is a function of yi t minus 1. Yi t minus 1 is a function of yi t minus 2, and it goes on, right? Each lag contains a certain level of information. If you're just using the second lag, you're missing out a lot of information. So is there a way in which you can incorporate all that into the instrumental variable? This is the question that we are asking. The answer to this comes from Arellano and Bond. Okay. Arellano and Bond gives an answer to this. We don't use Anderson and Hesiod model because of its limitation, because you can just use 2 lags. Okay, so Anderson and Hesiod's model has its limitations. The Holtz-Ekin's model gives a suggestion to overcome the problem of losing some observations, but the limitation still remains that you are just using the second lag. So what Anderson and Hesiod do, Arellano and Bond, Anderson's model has this problem. What Arellano and Bond do is that they come up with a model which addresses this problem. The problem that you can use only 2 lags. Anderson's models lag length limit restricted to 2 is overcome through the Arellano-Bond model. What it does is it includes a large number of variables. Okay, it accounts for more lagged variables. So when you're constructing your Z matrix, your IV, the instrumental variable, this is what you you construct a Z matrix which includes all available lags of YIT for each difference equation. This is the where is our difference equation? This is what we are looking at, equation number 5. Okay. Your Anderson-Hesiod model, Arellano-Bond model, Arellano-Bond and Brundle model is looking at this model. Okay. So remember this, it's a first difference model. So they come up with a solution to this. They come up with what you call as the first differenced GMM. Okay. The method is first differenced GMM. And what they do is, instead of just using the second period lag, they start using all the available lags of the untransformed variables. They started using lags into the picture. They bring into the picture. So what it does is the Z matrix, which was like yi1, 0, 0, 0, 0, they started using more lags. For this, the second one, what you're doing is you're using the second period lag as well as the third period lag. If you are using this YIT minus yi1 is YIT minus 1, this will be second period lag. And when it comes to the third one, you are going to use more lags. Okay, this is essentially what we do. So each column represents a lag that is used as an instrument for delta YIT. So our equation, you guys have noted down the equation number 5, right? No? To understand this, I want you guys to write down this equation number 5 so that you are following what I'm saying. This is the model that we are using, okay, for both Anderson-Hesiod, first difference GMM, and the system GMM as well. So the Z matrix includes all available lags of YIT. So in the previous case, what happened was you just used the second lag, right? You used only the second lag. But here what we are going to do is we are going to use all the lags that are available. If it is T minus, so this corresponds to T minus 2. This corresponds to T minus 3. This corresponds to T minus 4, for which you have 2 lags. When it comes to T minus 5, you have 3 lags. You understand what is happening? For T minus 3, you have 1 lag. T minus 4, no, sorry, T minus 2, you have 1 lag. T minus 3, you have 3 lags, right? Sorry, T minus 2, 1 lag. T minus 3, 2 lags. T minus 4, 3 lags. Okay, this is what is happening here. And this is how the specification looks like. Now, is this an improvement? Is this an improvement compared to the Anderson-Hesiod model? It is, because we are using additional information here. In period T minus 3, you are using how many lags? 2 lags. In Anderson-Hesiod's model, you are just using 1 lag, your YIT minus 2, right? How was the Anderson-Hesiod model? This one, right? Goes on. You are just using 1 lag there. Now here, you are using 2 lags for the period. So rho corresponds to each time period. Rho corresponds to each time period. So you are using, for when the time is equal to t is equal to 2, you are getting 1 lag, and it looks like this. Okay. So is the model better now? Is the model better now? It is. It carries more information. As the time period goes, as the, let's say the t is equal to 3, t is equal to 4, we are using more information. Okay. So basically what happens is that each additional lag will provide more information. But once you run this in a model, what will happen is that there will be an instrument corresponding to each of them. So the system is going to get complex. So here you are trying to estimate beta 1 and beta 2. If you include more instruments here, there will be a coefficient corresponding to these instruments also, right? For each lag, there will be a coefficient corresponding to that. Ultimately, this is a matrix, and eventually you are going to find the product using whichever model minimization strategy, right? The moment you include more lags, the system is going to become more complex, or rather, there will be a large number of instruments, but the number of beta coefficients might actually be less. For example, you're looking at a model beta 1 yi t minus 1 plus beta 2 delta x t minus 2. Assume that there is only x variable. If we go on constructing instruments like this, for corresponding to each instrument, we are going to get a value, right? We're going to get a value once you do the multiplication. We're going to get a value for this. So you will eventually end up with a lot of instruments, but the number of coefficients which you are more concerned about. What do you want in the model? You want the coefficient beta 1 and beta to be unbiased and consistent. But to get that done, when you do all this transformation, when you add all these lags, you end up creating more instruments, and you have a problem where the number of instruments are actually more than the number of parameters that you are looking at. Okay. But does it improve the efficiency? The answer is yes, because you are carrying information from the previous lags. Yeah, so basically, Arellano-Bond comes up with a set of assumptions. The first assumption is that the XIT is strictly exogenous. And this is the way you estimate this Arellano model. We'll get into the estimation part of this Arellano-Bond model. This is the way we are going to estimate. What we do is we create some kind of a weight matrix. We will see how that works, okay, which is a predetermined variable. And this is what we are going to solve eventually. And the assumptions, it's a micro panel. There is a linear dynamic relationship between yi and yi t minus 1, suggesting that there is autoregression of order 1. What is autoregression?
The term is related to its past value.
The term, the YIT that you are observing is related to past values. So autoregression. Autoregression of order 1 means it is related to its own lag 1. The argument is that in Arellano-Bond, there is a linear dynamic relationship between the YIT and YIT minus 1, but there is no relation between YIT and YIT minus 2. No direct relation between the YIT and YIT minus 2. But YIT minus 2 is included because that is YIT minus 1. Okay. Then exogenous. Then the unobserved heterogeneity is present. Heteroscedasticity and autocorrelations are there. How do you address heteroscedasticity? Well, you can use a VC robust function and then address the heteroscedasticity. Autocorrelation is there. But this heteroscedasticity and autocorrelation are within the individuals. Within I equal to 1 for the different time periods, there is heteroscedasticity and autocorrelation, but not across. This is what we are arguing. Okay. And if this is the case, how are we going to estimate it? We use the generalized method of moments. Are you guys lost? No? Or yes? No, if it is a no, you should tell.
Little bit.
Somewhat. Okay. So the whole point is we need to get an instrumental variable, right? We need to get an instrumental variable. That is the whole idea. Okay, one potential instrumental variable is this. The Z variable that we are talking about is this. Okay, argument is that this is highly correlated with X. The instrumental matrix Z that we are given in M1, the first matrix, is highly correlated with X. We are using instrumental variable because why are we using instrumental variables?
Endogeneity.
Endogeneity, right? So what we want is a variable that is correlated with X, but not correlated with. So we need to create another matrix instead of this. We need another one. Okay, we need another one. How are we doing it? One suggestion is create one like this. Create one like this. And what is yi1? yi1 is nothing but yi t minus 1 or delta yi t minus 2. This helps to overcome the endogeneity issues because yi t minus 2 is not related to epsilon it. Right? It is not related to epsilon it. So you overcome the endogeneity issues. Now, is this the best way to add? Is the best way to do it? Maybe this is for y. You are using yi t minus 2 as the instrument. Can you use yi t minus 3 as the instrument? You can use yi t minus 3, but you're losing one. So no, you're losing two observations. You are losing two observations. Is there a way to improvise the system? These are all dots. We're assuming that we cannot use this observation. What Olds and Ekin suggest is that put everything into 0. You will, but use only y t minus 2. Use only y t minus 2 as the instrument variable. So this is instrumental variable is what you are going to use here. Then the limitation of this model is that you are using 2 lags alone, assuming that 2 lags carry more information, but the other lags could carry some amount of information, right? So what do we do? That's where Arellano-Bond comes into the picture. Okay, what they are suggesting is that let's start with this model, the equation number 5, the first difference model. Okay, and then we will create instruments from this particular model. How are we going to create instruments? This is the way they are going to create instruments. How? Using all available lags of the untransformed variables. If t is equal to 2, you don't have any instrumental variable. If it is t minus 3, t minus 2, one instrumental variable, t minus 2, t minus 3, 2. That's the way it goes. Okay. You can create this one. Is this model better than the Anderson's model? Yes, because you are including more lags here. Okay, so definitely capture more info. As the time period increases, you are carrying more lags. So today's value depends on if it is y ti minus. If today's value depend on a large number of lags. Okay, as the time period comes down, depends on lags. Now we have a set of assumptions as well. Now we will see how we actually estimate this model. I mentioned that there is a Z matrix. I did not put that anywhere in the equation that I wrote, right? How do we incorporate this instrumental variable into our model to estimate beta? What we need an estimate for this beta using beta. This beta 1 is what we need to estimate, right? We are using instrument variable for that, but how exactly are we using the instrumental variables in this model to get this beta value is what we are going to look at. We are not replacing the x variable with this one. Remember that. We are not going to replace the x with the instrumental variable, but we are going to do some transformations there. Okay, understood that part? Yes or no? Otherwise, I'm happy to explain again. So have a set of assumptions. What we do is we use the generalized method of moments to do this, to estimate what? The beta coefficient. So we are trying to estimate what you call as beta GMM. We are trying to use a beta GMM. Okay. And we are going to estimate that beta GMM making use of the instrumental variables into the model. We are incorporating the instrumental variable into the model. We are not replacing the X with instrumental variable, but we are going to use the instrumental variables in the model and do some minimization technique, some arithmetic operations and some minimization technique, which will help us to find the beta GMM. I'm going to skip this part. Please remember that OLS can be estimated in multiple ways. The ordinary least square regression, the beta that you find, the conventional way to estimate an OLS regression is the sum of squared method. Minimize the sum of square of the error term. That is what you do, right? Minimization, summation of yi minus yi hat, right? And you are doing a minimization on that. That is one way to estimate the beta coefficient in an OLS regression. Similarly, you can use another method, which you call as the method of moments, where we use the first moment. Which is the first moment of a data? That is a mean. We are using the first moment, and we are using this kind of a transformation there. Okay. What we will do is we are going to set the mean value as 0. We are going to set the mean value as 0. And then we find out. So this is your linear regression. We are assuming this matrix. So that is the reason why I put capital letters. Okay. And the X is a vector. It's a vector of explanatory variables. And UI is your error term. You're assuming that it is exogenous, right? If what you need to find is the expected value of this, What is beta? What is beta? Beta can be written as yi minus this one, xi beta. Then this error term, what is this ui? Ui can be written as yi minus xi beta, right? So what we are saying is that this is a matrix yi equal to xi beta ui. Okay. What is the moment that we are looking at? The expected value of xi and ui equal to 0. No, they are not exogenous. What is ui? Ui will be yi minus xi beta. So we can rewrite this as expected value of xi into yi minus xi beta equal to 0. Okay, this is what we do here. And then you go ahead and solve for b. That will lead you to an estimate of b, beta hat equal to x prime x inverse into x prime y. Remember the equation for beta in OLS method, summation of a pretty lengthy equation that was given in Gujarati's textbook. I can't recollect that equation. Remember that lengthy equation, xi minus x bar the whole square. I mean, I can't recollect that equation. This is the same beta hat. Okay, the beta hat that you get, same, but we are using a different approach, using a matrix approach. So this x and y are matrices. Okay, we are doing a matrix multiplication and we are going to find what is beta hat. Now, skip some components. Now, what what we do in Arellano-Bond model is that we have an objective function. What is that objective function? Our objective is to find out beta, right? We need to find beta. We define a function for beta. Probably here. This is what we are looking at. This is what we are looking at. We need a function that will help us to find beta. Okay. How are we going to do this? What we do is we define a function. Okay, we define a function which looks like this. But there is a huge derivation behind this, which I'm not going to explain, but I'll tell you the logic behind this. You remember this transformation, right? Expected value of xi into yi minus xi beta equal to 0. Right? You're setting the first moment equal to 0. Here also the first part represents that. Okay, but here instead of xi, we are using the instrumental variable. So if you look at this, we took the first moment and set it to 0. Right? What we do is we use the setI, the instrumental variable. We bring the instrumental variable into the picture and do this transformation. We add another term. These are means. Why do we call this a method, generalized method of moment? Because you are looking at the first moment, that is the mean. Okay. Then what we do is we come up with a term W, which is a weight that is given, which is an arbitrary weight that is given. We will explain why do we need that weight. Okay, because when we are doing this matrix multiplications, you need a term for weight, which will capture the importance, which is basically to find out we need to find out what is the relative importance of each of these terms, each of the instruments. Okay, so the W captures that, and then again you have this one. Okay, so this is how it looks like. 1 by n summation of zi prime yi minus xi prime beta, the whole prime into W. What is W? It is a weight matrix. How do you choose this W? Use this function. Okay, you use this function here, and then you're multiplying it with 1 by n into z prime I into yi minus xi prime beta. Difference between the two is this. Yeah. Okay. And the weight matrix is chosen like this. Weight matrix comes from your instrumental variable as well as the error term. Okay. Now what do we do? Once you have the objective function, what you need is to find out what is the value of beta, right? So we are going to do a minimization here. We are going to do a minimization exercise here. So basically delta, what we will do is delta Q beta by delta beta. So we are going to do a minimization there. Oh, I mentioned it. And once you do that minimization, this is what you get. Your beta coefficient based on GMM looks like this. Okay. The beta coefficient that you use looks like this. Remember how what was the beta coefficient in Euler's model? In Euler's model, we were getting the beta coefficient like this. Beta hat is equal to x prime x inverse into x prime y. Now here, we have included the instrumental variables as well, along with the weight matrix, which is derived from this particular matrix, with this particular moment. Okay, from this particular moment, we are deriving the optimal weight, and we are using that here in the equation. Looks very similar to the equation for beta using the OLS method, but we are incorporating the instrumental variable as well as a weight matrix. Okay, so Arellano-Bond argue that using all the available lags as an instrument improves the efficiency of the model. This is what we were discussing. Why are we doing this, right? So include all the models. We are using all the instrumental variables. We need to incorporate it. We cannot replace X with instrumental variables. We need to incorporate it into the model. So this is the way we incorporate it to get the beta coefficient. Okay. Is that clear? Yes or no? At least understood the intuition behind the model? Okay. I will get into this part at a later stage, but Arellano-Bond has a set of limitations as well. Arellano-Bond, while this is a good way to estimate the beta, is this better than the beta that we got earlier? The beta OLS and the beta FE transformation, is it going to be better? The answer is yes, because we are incorporating the, we are getting rid of endogeneity. We are getting rid of the autocorrelation, right? We are incorporating more information from the lag values. So therefore, this beta GMM estimate is better than the beta OLS or beta FE. Remember, I mentioned that beta OLS will always be overestimated in the presence of endogeneity, and it will be underestimated when you are going for FE transformation, right? Where will this be? This is going to be somewhere in between. This coefficient is going to be somewhere in between, okay? Because it is overcoming the problems that we discussed. The Arellano-Bond model overcomes both the issues that we were discussing. So this estimate is going to be better, but this need not work all the time. Specifically, if YIT is highly persistent, means if beta 1 almost equal to Y, beta 1 almost equal to Y, what does that mean? When this beta 1 equal to 1, delta YIT minus 1, oh, exactly the same as delta YIT, right? Indicating what? What does that mean intuitively? It's almost a one-to-one relationship. Past value is deciding what is the present value, right? So if your beta coefficients are equal to 1, once you run the model and if you find that the beta coefficient is equal to 1, it simply suggests that there exists a persistence. What happened in the past is deciding what is happening currently. So ideally, we would want a beta which is less than 1. It should be between 0 and 1. We want this one which is much lesser than that. Okay. So if the beta coefficient is highly persistent, Arellano-Bond need not be the right way to do this. Then there is also an argument that it has poor predictive power, depending on the lag levels. You can use lag, but there is no guarantee that the lags, adding more lags gives you better estimate always. Remember this, you are adding more instruments. When you are adding more lags there, you are adding more instruments, right? Now, if your instruments are much more than your coefficients or your parameters, again, you have a problem there. So Arellano-Bond comes across this problem. Okay. How do we solve this problem? That's where system GMM comes into picture. Okay. System GMM was given by Arellano and Bover in 1995, and later we have a Blundell-Bond model. We will look at the Blundell-Bond system. Okay, both use a similar approach. What it does is we need to capture as much information as possible from the lags and the differences, right? From the lags as well as the differences. What it does is, why do we call it system GMM? So basically, it considers two equations. One is a level equation. YIT is equal to your level equation. YIT is equal to, I have given the term rho here just to differentiate between the two so that you use it. yi minus 1 plus beta 2 into xit plus beta I plus epsilon t. So we start with these two equations. This is the level equation, and then you also take the first difference. So Arellano-Bond used which one? The first difference model. In the system GMM, we are using the level model also. Level model also. The level equation is also used. That is the reason why we call it a system, because there are two equations that you are looking at. Okay. So is it better, or will there be any advantage of using the level equation also along with the first difference? Yes. Okay. Arellano-Bond used this model, right? Then they go ahead and construct the instrumental variables. And we have a transformation and minimize. We find the function for the quadratic function for beta. We find the objective function, so not the quadratic, the objective function for beta, right? You do a transformation to find your beta GMM. You use both the instrumental variables x as well as the weight matrix that is derived from the formula that was given earlier, right? Now, what happened here is that we just used the first difference model. Arellano-Bond just uses the, oh, that equation was missing from the slide. Arellano-Bond just used what we were describing here. Arellano-Bond used this one. Okay. They go ahead and find the instruments based on the difference model. Okay. Anderson and Heseo also do the same thing, first difference model. But what we do in system GMM is to look at the original level equation also. Okay, original level equation also. But we know that this level equation has a problem, or the two problems. But if we can consider these two, level equation and difference equation in one system, and if we can overcome the problems that we discussed in both of them together, isn't that the best model? Isn't that the best model? Level model has problems because endogeneity and autocorrelation. You need to overcome it. Well, Arellano-Bond suggested a method to overcome it, right? But now, can you incorporate this level equation also into the picture and come up with a solution that will help overcome both the problems, right? If that is the case, then this is much more efficient. This is much more efficient. The beta coefficient that we are going to get is going to be a much more accurate representation of the variables that we are looking at. The relationship that, not the variable, the relationship that we are looking at. How do we, so it's going to be a system of equations. Okay, it's going to be a system of equations. We are going to construct instrumental variables. And this instrumental variable is going to be even more complex. Because we know that for the first difference model, we have to use instrumental variables. Now, level equation, well, it still has endogeneity and other ones. So there should be a way to overcome that. We again find some instrumental variables. Club it together. So it's going to be a much bigger instrumental variable that we are looking at. This is what we do in the system GMM. Okay, so we consider both these equations. Now, if you are taking the level equation, we need to create a instrumental variable for the level equation. How do we create instrumental variable for the level equation? What we do is we use the lag differences for yi t minus 1. We use the lag differences for yi t minus 1. And for the first difference, we are using the lagged levels of delta yi t minus 1. There's a small change in strategy. Okay. So we are finding the lag differences for yi t minus 1 in the level equation. Lag differences for this yi t minus 1 in the level equation. And here, in the second case, in the first difference model, we are using the lagged levels for delta y I t minus 1. This is what. So we are going to introduce two types of instrumental variable into the picture because you are considering it as a system. How will your instrumental variable look like? Arellano-Bond's method is already there, right? The Arellano-Bond, the instrumental variable you have already seen. We are going to add this into picture. This also into the IV, right? And you are going to create one single instrumental variable. How does it look like? This is the way we are going to construct for the difference equation. This is your instrumental variable. You're familiar with this one, right? Now, remember that each row corresponds to a difference equation because that is what we were doing in Arellano-Bond model as well. Okay. Then we use a levels equation. We use an instrumental variable for the levels equation as well. Arellano-Bond plus a set of instrumental variable that addresses the issues with the level equation as well. And it looks like this because you are taking the differences. You remember what I mentioned here? We are using the lag differences for yit minus 1. What we do is do this difference equation. Since it is a system of equations, we are going to add this as well, which will eventually give you an instrumental variable like this. Okay. So how will this instrumental variable look like? So it goes like this, okay, and levels start here. So it's going to look like a giant matrix. I mean, I did not have the patience to sit and write down that matrix, but this level matrix, whatever you see in the level matrix comes here. Whatever you saw in the difference matrix also comes here. So it's going to look like a big this one, which also indicates that there will be a large number of instruments. There will be a large number of instruments. Now, will this work? Large number of instruments comes with a set of other problems also. What if the number of parameters that you are estimating is less, and what if you have more instruments? Right? What are these instruments? Ultimately, lags or differences. Right? Ultimately, they are lags or differences. Now, the question is this one. What is that optimal number? What is that optimal number? Well, the model will help us to estimate this. We'll see how that is done. Okay? I'll take you through the data, the way you work on it. But did you understand what is going on? The intuition behind the models. I haven't given all the mathematical derivations. It is going to take much more time if you want to sit and do it. You can refer Beltagi's textbook. Beltagi has given a textbook, and for this system GMM, I think go to the original paper of Arellano-Bond. That is the best reference material for that. But as long as you understand the intuition behind these models, I'm okay with it. Rest of the math we'll figure out. Did you understand or not? What did you understand? Can someone explain what is going on? So make an attempt. Let's see. If you make a mistake, it's absolutely fine. I will start the story saying that we have a dynamic model. Our OLS estimates and the FE transformation doesn't help us. because the estimates are going to be biased and inconsistent. What do you do?
Various approaches to address this problem of endogeneity.
Yes,
Like each is an improvement of the other.
each is an improvement of the other. Okay, but what is that approach?
The meaning other one is.
Demeaning is that my story starts there. We have done demeaning. It doesn't help. What do you do after that? What do you call that? Instrumental variables. You introduce instrumental variables. Okay. So it all depends on how you are going to treat those instruments. These models tells you different ways of creating the instruments that will overcome the endogeneity issues. This is what I'm trying to tell. Okay, you use instrumental variables, but each method gives you different ways of creating instrumental variables that will help us to come up with a beta coefficient corresponding to this persistence. What you want to know is the persistence. This is what you are trying to figure out. Okay? You want to know how much the past values are affecting the present values. Right? You want to know the persistence. If there is no persistence, need that. You don't need it. You don't need that YIT minus 1 in the picture at all. Right? You might be able to run an OLS and as long as there is persistence, well, you need to use some instrumental variables. How are you going to construct instrumental variables? That is the question. We have a couple of methods: Anderson and Hezeo, Arellano-Bond and Arellano-Bond system GMM. Arellano-Bond's method is called as
Difference
GMM. Okay. Now the question is, how are you going to construct the IVs? How are you going to construct the IVs? How did Anderson and Hezeo construct the IV? They suggested that you can construct an instrument based on the lags. How many lags? It suggested using the second lag. What is the advantage of using the second lag? Because the error term, the endogeneity disappears, right? Instead of using YIT minus 1, think about using YIT minus 2. Endogeneity disappears, but Anderson-Heseo's problem later was modified by Holtz and first approach suggests that if you do that transform, you can create an instrument. The instrument is either YIT minus 2 or delta YIT minus 2. The problem is that one observation will be lost, right? You do not want to lose that information when you are running the model. How do you do it? Holtz and Ekin suggested that, well, put a 0 everywhere, then use that in the model so that we still have the relevant information. We don't lose observations. Okay. But then they also suggested that usually the second lag, only the second lag for everyone. But that is not a good approach, because in the instrument you are using only second lag, assuming that second lag carries the maximum amount of information. We are not removing x1, the other variables from the picture. Remember that, okay? So, so we put a 0 everywhere so that it is a part of your instrumental variable, and still we use it. But then you are limiting it to 2 lags. So all the information is not used. Okay. It has something to do with the orthogonality condition, which I'm not getting into. Might take some more time to explain it. But remember that this is the essence of the story. What did Arellano and Bond do? They are adding. Their first thing, they tried to remove the restriction that you can use only the second lag. How did they approach this problem? they used this method to construct the instrumental variable. They used this method to construct the instrumental variable and used this instrument in the estimation of beta. Okay, we have a conventional way to find the beta coefficient, the one that you read in Gujarati or the one that I showed here in the matrix form. Okay, I'm explaining it in the matrix form. We use this instrumental variable in the model, and what they do is they use this GMM objective function. This is the objective function that they are using. Unless we had an objective function, right? We are trying to set it to 0 when you're using the method of moments. Here, what we are doing is we are trying to minimize this with respect to, and we have a weight matrix as well. And this is the way you arrive at the weight matrix, where you find the summation of Zi, the instrument, into the error term. Okay. So you have this weight matrix as well. Weight matrix as well, and then you estimate this. Minimizing this function leads to this equation. So we are going to estimate this equation in the case of Arellano-Bond. So in the OLS, it was x prime x inverse into x prime y. Here we are including the instrumental variable, the weight matrix. Okay, that eventually leads to this beta, and it is a better estimate because you are including more information, more orthogonality conditions. Now it comes up with a set of problems as well. Especially if your beta is highly persistent, this model need not work. This need not work, and we really do not know the power of the lagged variables. In some cases, the lagged variable need not carry enough information to be included in a model. You're adding more instruments, right? You're adding more instruments, but are all those instruments relevant is the question. So it comes up with those limitations. Again, once you estimate Arellano-Bond, we typically, so our objective was to figure out if there is, our objective was to remove autocorrelation as well as the endogeneity issues. Endogeneity issues leads to overfitting, right? Autocorrelation brings down your estimates. What we do is once you test this Arellano-Bond model, we do a test for autocorrelation. We do a test for autocorrelation to see if there are second order, if there is an AR2 term also. The condition is that you need AR1, no AR2. We do a test, and we do a Sargent's test to check if there is overfitting. You have included so many instruments, right? Your parameters might be less, instruments are more. Is it into overfitting, or did it just solve your problem? The answer to that comes from Sargent test. Okay, you calculate the Sargent test calculates, and yeah, that is the first Arellano-Bond. Then comes system GMM. System GMM is an improvement over Arellano-Bond. What it does is that it incorporates the level equations also, and to overcome the problems with the level equations, it adds more instruments. It adds more instruments. What are the instruments that level equation adds? Look at the lag differences. And what are the instruments added by the difference model? Here you are adding the lagged levels. Okay. That is what is given here. This is the difference, yi1, nothing but yi1 minus yi2, right? This is the differences, okay? And what is this delta yi2? This is for the level equation. You are adding the difference. Total instruments will be a combination of these two. It is coming as a system of both the equations, and you are clubbing everything to come up with a new instrumental variable. And this instrumental variable adds more instruments, but at the same time, it adds more explanatory power also. We again go ahead and see. We have a test. We have a test for autocorrelation as well as a Sargent test, because you are adding autocorrelation has to be eliminated. We are checking once we do the model if the autocorrelation still persists. We don't want that autocorrelation, right? We have an Arellano-Bond test for that, and we have a Sargent test or a Hansen test to see if adding so many instruments is actually leading to an overfit in the model.
Sir, this Z difference and Z system are two matrix are there.
No, they are a single matrix. I mean,
No, after that, yes.
so what you find here,
This is one matrix.
this one should come here. So
One matrix and Z level is the another matrix.
basically should look like this.
Yes.
The rest of the matrix, it will look like a giant matrix.
Product.
Ah.
Matrix multiplied by matrix.
Yes, it looks like something. It looks rather a big one. I wrote this so that it is easier. Saves time to type. We understood the logic, right? Fine. Now, shall we go ahead with, and we need to do this test. Arellano-Bond as well as, sorry, the Arellano-Bond test for autocorrelation as well as. Because ultimately we did this because there was autocorrelation and androgenite overfitting. We want to see if these two disappears. Okay. Now, data in this. How will I?
So you will join the team here and you will share this screen. You see the link and then the link to the his laptop. You can connect your laptop. Account sharing and even.
Forwards to that system so that I don't have to.
Sir will join us.
I don't want something between this.
Or you can share my laptop people.
So we are going to use the original data by
Still have energy to go ahead. How much is left?
we are going to use data that is already available with Stata, which is the original data that is used by Arellano and Bond. Are you all on Stata? Are you connected to internet? Is it possible for you to connect to internet for a moment? Huh? There is one simple code that you can use to. There is one simple. This one you can use to. I can see the network. There is one simple one line. Web use AB data. Web use space AB data comma clear. If you can connect your hotspot. Web use WEB space AB data. You have done something prior to that. Put a comma and clear it.
Clear. Sir was saying earlier, if you have done something, then clear.
Yes, sir. I'm fine. No, yeah, I will join the meeting and I will share the screen. I am joining. Okay.
No, I share my screen, but I just need.
Yeah, I will start also, so not a problem.
We have Stata on your system.
Ah, yes.
ഓൺലൈനിൽ ഉണ്ടാവും ഡയറക്റ്റ് എടുക്കാൻ പറ്റും ഇതിലാവുന്നുണ്ട് പാക്കേജ് അത് എടുത്തിട്ടുണ്ടെങ്കിൽ നമുക്ക് ഈ യാഹൂ ഫിനാൻസിൽ ഡയറക്റ്റ് ആയിട്ട് ലൈവ് മോഡലുള്ള
If we could not use comma clear.
ഇതില്ല പോട്ടത് ലാസ്റ്റ്
என்ன பண்ணீங்கன்னு நினைக்கிறேன் ஈவினிங் எனக்கு சொல்லி கொடுக்க ஈவினிங் ஒரு ஹாஃப் அன் ஹவர் ஒரு கவுண்டரா எனக்கு ஒரு சம்மரைஸ் பண்ணுங்க
Internet is not there. Internet is not there.
Mobile is not working.
ഇത് ഇവിടെ വന്നില്ലേ
Registry, young
I already joined.
You have Stata there?
Ah, yes.
Yes,
Projector is okay. Madam, how you put the projector?
Sir, actually, when I joined, I shared my screen.
So how it is visible?
From here, it will be visible, sir. Because we have already joined online. So yours here.
Okay.
Network.
So I am sharing my screen.
Stop sharing here, you screen here.
Okay.
Yeah, so you share yours.
The pen drive there. Only pen drive it is.
You have data, right?
Start. Firstly, I will. Can I share again?
Use the mic, right?
വിഐക്ക് റേഞ്ച് ഉണ്ട് എയർടെലിന് തീരെ ഇല്ല രണ്ടും
Can you see the data screen? Can any one of you confirm? You should be able to see.
Yes, sir, we can see.
Okay, so what we are going to do is we are going to see how this is to be run. We are going to use the original data by Arellano and Bond. Okay, so what we do is we are going to pull this data from the data. Okay, we are going to use. We're going to pull this data from the Arellano-Bond package. There is a package called as a bond. We are going to use that. So we are going to recommend web use AB data. Yeah, I'm using, oh, don't have to use clear, but yeah. So
Did we use coma clear?
because you were already in a workshop, my assumption is that you were doing something before. Some data set is there. If you use clear, it will not use that data set. That's all. And somehow by default, when I type it counts. Habit. Okay, so now this data set, take a look at this data set.
Connection.
If we take a look at this data set, this is how it looks like. Okay, you have a set of identifiers. There are around 140 I's here. Then you have some year. There is an year variable as well. Okay, so we have a panel data here. And what we are trying to do is, what are the factors that drives current employment? Okay. Current employment, we are arguing that current employment depends on past values of employment rate or employment rate, whichever you choose, plus wages, plus the capital stock, plus the industry output. It is quite possible that while we agree that employment depends on the previous year's employment, so the unemployment rate is connected to the previous year's the past unemployment rates. Along with that, we are adding three more variables: wage, capital stock, as well as industrial output. Okay, the output by the firm. Now, it is quite possible that the lagged values of capital as well as the industrial output also affect the employment. Okay, the lagged values of capital as well as the industrial output or the wages also can affect employment. So you may have end up with a model which uses the past value of employment plus wage, the past values of wage, the lagged values of wage, plus the lagged values of capital or the industrial output. Now, what they have done is the variables that we are going to use is not this employment. I guess this employment. This we are not going to use this. You've done a log transformation of the variables. You've done a log transformation of the variables. N stands for employment. W for wages, K for capital, YS for output. Okay. Converted this into log values. We are going to use the log values. And of course, we have created the lagged values as well. NL1, first lag of YI. NL1 is what? Your YI, T minus 1. NL2, YI, T minus 2. NL1 corresponding to this N in this particular period. Right? Then similarly, we have done for a few the other variables as well. The argument is that it could, the past values of capital as well as the output could affect the employment. Okay, got an idea. And then we have a couple of year dummies as well. We have included a couple of year dummies as well. Okay, can you guys, so what did we discuss? We said that we can run an OLS model, but the OLS model is going to be biased and inconsistent. We have endogeneity issues, right? So let's first try to run an OLS model. How will you run an OLS model on this? First, set it as a panel variable. How do you set it as a panel variable? XT set your ID and year. Setting it as a panel, and it's an unbalanced panel. Why is it an unbalanced panel? Because we have taken lags. To understand the missing values that we were talking about, right? Now it makes sense. But when I put a dot, when we constructed an, yeah, so this is what we were talking about. Whenever you take a lag, one observation goes missing. Okay. What did Holtz and Ekin suggest? It as a 0. Okay. Now, what we are going to do is we are going to do a simple regression, simple OLS regression. Okay. I'm going to regress N, okay, to a couple of other factors. Let's say N, W, K, Y, S. Okay. And I'm going to, so in the model that I have written there, I haven't used any time effects. The mu T that you studied, I haven't included any time effects. What I'm going to do is add a couple of.
Do we have to take N twice?
Oh, sorry, did the N come twice? Remove one N only. So your dependent variable followed by your independent variable, and we are going to add a few year dummies because we want to account for the time effect as well. Okay, we did not consider that time effect in the model, but we are accounting for that. So we are going to add the time dummies from Am I audible to the people online?
Yes, sir.
Yes, sir, we are doing.
Yeah. So then I'm going to add the dummy variable to add the year effects.
Increase the time. Otherwise it will close down and
Okay. So I have added all these variables. I can estimate a model with the past values as well. Okay. I can add the past values of the lag variables as well. So here we get some lags. We have a couple of lags. Or let's say I'm going to add these lags as well. Let's estimate a full model. I'm adding all the lag independent variables as well. Now let us run this regression. What do you observe? Oh, no. You have missed one important parameter. What is that? L dot N. You have to add an L dot N also. Why? The lagged value of N. We missed adding the lagged value of N. So what I did is I have the dependent variable here followed by lagged value of n, and then the time dummies as well as the lag values. I just added everything that I could get. Okay. Wait to zoom it.
Sir,
L dot n. What is L dot n? L dot n will give you the lag value of any number. D dot n, first difference. D dot n gives you the first difference. L2 dot n, second lag. D2, second difference. Okay, we're going to run this regression. Is there a way in which I can zoom it? Anyone knows how to zoom this?
It will not. We tried yesterday, but
Sir, actually, we can.
I'm going to run this regression. This is what I get. This is what I get when I ran this particular model. This is what I got when I ran this model. Okay. What do you understand from this model? What is the variable that we are interested in? What is the variable that we are interested in?
employment.
Okay. Which employment?
Right click if you do font, then it will increase.
Right click. That also means that the okay.
So in command window also do the same.
Commandment, this one also I can do the same. Why is 1976 not included? There's a trap. Because all of them are year dummies, right? If you include all the years, you will come across dummy variable trap.
why they are not taking 1976?
Dummy variable trap. Here also I can increase the font. Great, thanks. Okay, now what is your observation from this? Take a look at the result. Tell me what is it? What do you think it is? What does the coefficient tell you? The beta 1. Which is the beta 1 here? Which is the beta 1 here?
04.
1.04. So the beta is close to 1. Beta is close to 1. Okay. And you know that OLS is overestimating the results, right? When you do an OLS in a dynamic panel, it overestimates. So this beta 1, which is the measure of persistence, the impact of past value of employment on current value, is overestimated by the OLS. So the true coefficient of your so the beta coefficient should be much lower than this, right? In that case, what do you do? Can you guys try doing a fixed effects model? How do you do a fixed effects model? Use XTREG. Yes. I will do that. Can you see that? Can you come front? Which one? Oh, this one. That is okay, because some of them got omitted because of the dummies typically gets eliminated if there is any multicollinearity. Yes.
AB data.
Put a comma there. No, when you are putting the stata codes for OLS, just first you the one that you put first by default is taken as the by default is taken as the dependent variable. Okay, you don't put commas between the codes. So the logic that Stata uses is that you're going to regress the first variable that you use by default is treated as the dependent variable, and whatever comes after is treated naturally as the independent variables. Okay, can you try doing a fixed effects model? What do you observe?
It comes down.
What is the new coefficient? How do you do the fixed effects? XT-reg and do the same thing. And so I'm going to next do a fixed effects model. I'm just going to use the same variables that I used. XT-reg, and then I'm going to use FE. What do you observe when you do the FE? Oh, so for the people who did not understand the command, this is what I did. I took the same, we are running the same model. Okay. Only change is that we are converting this regression into XT regression, indicating panel regression. I added a fixed effects here. Okay. This is what I did. Now, what do you observe? What will happen when you do this? The FE transformation.
R,
The value of beta
97.
comes down because FE is underestimating your model because of the negative correlation that we discussed earlier, right? So then what do you do? The next one is what we can do is we can try doing an Anderson-Hesiod estimator. Let me just see if I can. For that, what we need to do is the next step. That next thing that we are going to do is the Anderson-Hesiod estimator. What exactly do we do there? The Anderson-Hesiod, what exactly do we do?
Second lag.
Second lag of what?
Instrument variable.
We have to create the instrument variables. So how do you do that? How do you do that? You have to use the regression command using instrument variable, which is nothing but IV-reg. There is a command called as IV-reg. What we do is we are using the IV regression, okay, or rather IV regress, and we are using a two-stage least square. Remember, mentioned that we are going to use a two-stage least square. First, you run the regression, take the difference, and then you use that difference in the model. You are running a USLS. You remember that the presentation that I mentioned that, yeah. And then what do you do? Hold on a second. I'm trying to see if you can. We have to create the first difference variables, right? That is not created. Let me see if there is an easy way to do it. If you can do it without creating the first difference variable. Otherwise, we have to sit and create all the first difference variable, D for N, D for Ln, D for W, D for K, D for a couple of year dummies as well. Give me a minute. I will just see if we can do it without that.
എന്തിനാ most of the people in the ஆனா இது போட்டு புரியுதா எல்லாம்
We'll skip that step for the time being. I'll directly get into the same time. We'll directly get into the Arellano-Bond. Okay. Now, Arellano-Bond, I'm just skipping this. Otherwise, we have to sit and create the dummies. So what we are going to do is next do the Arellano-Bond estimator. Now, the Arellano-Bond estimator, we have to add the instruments as well, right? We have to add the instruments as well, but we don't have to do it directly. So there is a command called as XTA-bond. Okay, we are going to use the XTA-bond command. Okay, what is A-bond? Arellano-bond. What is our expectation? The coefficient that we get through Arellano-bond lies between the OLS and the fixed effects. So I'm going to use the XTA-bond command. Okay. Now, we don't have to give much specification. The only thing we need to do is to just put the first your dependent variable, which is N. Then let's include a couple of other variables as well. Which are the other variables? There are other variables that you can use. There are other variables that you can use.
WKXTA-bond.
Now, before doing that, let's specify the lag structure. We will specify the lag structure. How many lags we should use. So for that, what we will do is we will add a function called as L, and we are saying that we will use the 2 lags. The yi t minus 2 that we were talking about. Remember what we do when we create the instrument variable? We are creating the yi t minus 2 as the IV, right? So we will specify that that is going to be the IV. That is going to be the structure of the IV. Okay. Then what we do is we will specify our explanatory variables. Now remember this, okay? I can go on adding all the variables. But is it going to be good or bad? I mean, the moment you are adding more variables into this model, you are adding creating a much more complex system, which will eventually lead to a large number of instruments. Do we really need all of them? So anyways, let's start with this. Let's start with just 2 of them, W and K. Later we will add more. We will just start with 2, and then once you're familiar with this, we will add more this one. Then we will add some selected year dummies. We need not add all year dummies. Let's say I add the year dummies from I'm just trying to limit the sample, okay? Because you know that the moment we add more variables, you also add the year function as well. We will try the VCE robust to adjust for. Why do we use VCE robust? Robust estimates or heteroscedasticity. So you understand, in the estimation procedure, we can account for heteroscedasticity. That's the reason why we really did not worry about heteroscedasticity in the model. I'm just going to take a sample and do it. Okay. How many instruments do you think will be created? How many instruments will be created? The reason why I'm not putting all of them is because it is going to create a lot of instruments. We don't need all of them. So once I run this.
Why did you take year variable? You're taking time down.
You can do it without that also.
Year comma.
I took the year specifically. You can run it without that also, not a problem.
ECE.
Now,
ECE.
now take a look at this. Is this model a good estimate? Is this model a good estimate?
Thanks, sir.
No. It is not between FE and. Now what do you do? What will you do?
Can you go to the command?
GFM is left. It is between FE and voltage. No, that was 0.73. That was 1.
No, so it should be between 0.70 and 0.1.
1.
Between 0.7 and
It has to be between. It has to be between.
73 and 1.
So why are we getting this number here? The reason is that the model specification. The reason is models will be just used a few of them. Now, why did I just use few of them? Just to show you that when you ran this model, it around 40 instruments already. It generated around 40 instruments. Okay, is that way too much? Is that way too much? How many parameters have you got? How many parameters have you got here? 1, 2, 3, 4, 5, 6, 9, 10, 11, 12, 13, including the constant, right?
Yes, sir. Start the
Now, which are the instruments that were created? Which are the instruments that were created? That is given here. That is given here. These were the instruments that were created. How many instruments are there here? These are the instruments that we specifically asked the model to build. But then, because of the Arellano-Bond transformation, right? The IV method that we are using, it led to a creation of 40 instrument variables. How do I know that there are 40 instrument variables? It says number of instruments is equal to 40. Which are those 40 instruments? A few of them are given here. 1, 2, 3, 4, 5, 6, 10, 11 are given here. What about the rest? The rest is coming from the GMM. Because these are the ones we specifically asked for. And the GMM, and for that, given that we have given a lag of 2, it has created a set of instruments. For the time period T minus 3, there was 2 instruments. Time is equal to 4, there were 3 instruments, right? Add all, and we have added only a few years, right? all those instruments are automatically generated by the GMM model. Time constraint. I want you guys to go back and experiment with this. Okay, which one could be the best model? We start with 2 variables, add a few variables and see. Add a few more variables and see which one explains the data better. Huh? No, no. So now what you need to do is add the number of variables. We added W and K. A couple more. Add a few more and see. Because there were a lot of other variables that we used in OLS and FE, right? More variables, year dummies. Some extent. Now, real life, how will you do this problem? I know which are the theoretical argument which suggests that which are the variables that actually affect. I just took 2 of them to show you how many instruments are created. Do the rest. Add a bigger model with more explanatory variables. What you will eventually find is that your beta coefficient is going to go up. Okay, and it is definitely going to be above what the FE suggested, and it is going to be below what the OLS method suggested. Okay. So will you go back and experiment with this? I will share a couple of materials. You can share some materials. Right?
Can you share the PPT?
I will share the PPT. I will share some of the materials as well, where you can actually go ahead and try which model suits better. Okay. Then the next model is, which is the next model? The next model?
GMM.
System GMM. The code for the package that does this system GMM is XT, BP, DS, YS. XT panel, BP, DS, YS. Dynamic panel data system, DPD. Dynamic panel data system estimator. Okay. Again, we can use the similar approach. We will put our explanatory variable. Okay, explanatory variable. Then we can specify the lag structure L0. Why are we doing this? This is the specification for the instrument variable. The specification for the instrument variable, because we are using yi t-2. Start with that. And then this one dot, what you need to do is WK. Then use the year dummies, year 19, 0, 19802. Add the year variable also for us. Robust. Can run this model. What is this? 1984. Now you see what happened to your estimates. Has it increased?
Share the do file, don't.
I will share the do file. Share the do file, okay?
जल्दी करो उठा रहा है
Has the estimates improved? Is it looking more realistic than the other estimates? OLS suggested that it's a contemporaneous relation. I mean, it's one-on-one. The persistence is large, right? But here what you find is that there is persistence. The previous value of employment is affecting
Don't know.
today's employment by a factor 0.822. Okay. Now we can do the autocorrelation test as well. So here also you can experiment with the data. Okay, you can experiment with the data. Go back and do it. I will share the do file. I'll share it tomorrow morning. Let's see what they do. Make sure that you ask them what it is.
Yes,
Let's
yes.
see. Right? Yeah. Okay. Now the next thing is to do. So there are two post estimation commands. Okay. Here also you look at the number of instruments that are created. 47 instruments. 47 instruments were created. And where are those instruments coming from? These are the instruments coming from the specification that we gave, and these are the instruments that were created by the model. Remember that the whole metrics and the IVs, right? This comes from this GMM. Why did the number go from 40 to 47? Why did the number go up from 40 to 47? Because in Blundell-Bond, you include the system as well as the level equations, and you create IVs for both. You remember the big metrics, right? That is what is happening here. Okay. How do you, so there are two post estimation commands. One is A bond. So Estat A bond. Estat A bond. Estat A bond. That's for the autocorrelation. That's for the autocorrelation for lags 1 and 2. Should there be autocorrelation? There should be AR1. There should not be AR2. That is what you see here. I will share the PPT. I have mentioned the null and the alternate hypothesis. Just go back and check. Okay. Also, the next one is for overfitting. Oh, this suggests that the model doesn't suffer from any autocorrelation issue. Oh, well, this is only for the system GMM. Okay. After running Arellano-Bond on the same command, save it as the AB estimates for autocorrelation. You can use the Sargan as well. Estat Sargan. Just try Estat SARGEN. I think I'll end with this. I will share the do file. For those who are online, that is okay. Okay, so you guys just try this Estat Sargan. It's for overfitting. Oh, okay. So there's a small catch with the Sargan test. You cannot run the Sargan test when you have used PCE robust. If you're accounting for heteroscedasticity, you cannot run it. So why don't you run this model, the dynamic system GMM, without Python, I was supposed to teach it. That's where I started. So I learned with the students. But what you need to remember is that the tool that you are using doesn't matter. Okay. What you need to know is the process. What you need to know is the process. If you understand the process, tools are super easy. A simple example, why I am telling you to use Python. Because we are in the age of generative AI. Python has integrated all this copilots to it. For example, you go to Google Colab, that is an interface to run Python. If you have a Gmail account, you can open Google Colab. That's an interface to run with Python. Okay? They have integrated Gemini, large language model of the ChatGPT equivalent of Google into Google Colab. Data, plot it, see if there is issue, if there is no stationary, if it is non-stationary, use the lags or use the first difference. This one, you have a few tests to check stationarity, Phillips-Perron, ADF test. You know the sequence of doing an ARIMA model and eventually to forecasting. So I wrote all the codes. Last year when I was taking a session on time series models, I just opened Python, put a prompt. That's all. 5 minutes. What took me almost a day to write all the codes was done in 5 minutes. Told to extract the data from Yahoo Finance. ARIMA is a very simple case. So took the data. The prompt was very simple. Take the daily prices of Bitcoin for the last five years. Plot the data against time. Look for stationarity. So I gave the test name, ADF Phillips-Perron test. And after that, I asked it to run the ARIMA model and tell me the order of the terms, AR, MA, right? And what if it is, it had to be differenced. Okay. I added one more line based on this, put a forecast also. Okay. That's all I did. What I wrote in one day, getting it in this one. So it is important that you also start making use of this in your research. It is going, believe me, it is going to take a lot, save a lot of time. But what is important is understand the process. This is something I keep telling some students. There are people who can run codes. Okay? They run super machine learning models. But if you don't understand what is happening behind, no point doing it, right? So try to understand the logic, and Python also follows a logic. If you learn Stata, I mean, how many of you are using the drop downs? Or you type the codes? Type the codes, yeah. But Python and R follows a logic. Okay, so given that you have this large language models incorporated into it, Python is much easier. Okay, these days, whenever I run a model, I have migrated the whole thing into Python. The reason, one, I can use the steps are known to me, but if there are any errors, I can create a prompt that itself will fix it. I'm sure many of you, when you are using Stata, you sit hours to figure out what is the error, right? I don't do that. I don't do that. Okay, so it's not a very difficult thing to do. As long as you understand the process, it is going to be easy for you. If you have any doubts, you can reach out to me. Happy to help. Do you guys have any questions?